Buenas tardes, queridas colegas. For this final meeting of our successful project, let me share some experiences that are related to innovation and interdisciplinarity, which I believe are key issues or key principles also related to universities. So let me begin with a quote Albert Einstein made regarding problem solutions. He said, we cannot solve our problems with the same thinking that we used when we created them. Which in other words means that to create an optimal solution or the best possible solution, we need to step out of the usual, to think out of the box, but also to observe a problem from various perspectives, which means from various disciplines. Now, I believe that universities should also encourage and teach students for innovative thinking and problem solving, not just deliver the knowledge professors have or the knowledge captured in some textbooks. To emphasize these principles, I would like to present three cases. And first of all, the problems that we have in various projects solved, hopefully, in a creative and innovative way. First is inefficient monitoring of construction. This is a huge problem, and until today, or in the published sources, we couldn't find a really effective solution to this problem. So I will introduce a system that I think does solve it through automated continuous construction progress monitoring. And then the second case will be more specific and related to especially to bridge inspections. And the third problem will be more general, related to building itself, to constructing buildings, where we know that construction is quite a polluting industry. Only the production of cement does produce an immeasurable, or not immeasurable, but huge amount of CO2 and other polluting materials, chemicals, particles. On the other hand, we have lots of waste, also hazardous waste, that remain after a building is finished. So let us first go to the monitoring. Here we have looked to the problem from another perspective than the other researchers, who tried to actually capture or use images, capture the state of the building and at the present moment. What we did was to focus on those who introduced changes on the building, meaning workers. And if we can capture each changes while it's introduced, or identify every element at the moment when it is being built, or in any way mounted onto the building, then we of course can have the state of the as-built construction in real time. So each of these workers needs to scan the working area and thus the system is able to identify elements as they emerge at their final position. This is the basic principle. So in this case, we can create in real time a four-dimensional building information model. And this is actually the final goal. Now, of course, we did so we developed an architecture that is based on this identification using a partial point cloud and a building information model. And each of those scanners are then producing lists of identified elements. They're merged into a single list, and this list can then be graphically represented. I won't go into details about how the system works, but there is a part on the local level and a part on the central level, and as mentioned, the final goal and the final result is actually the list of all elements that are standing on site. In the prototype, we used some available technology like the structure core scanner, the Raspberry Pi Zero that can be easily built into a protective helmet, some software that identifies the elements, and then server software which then merges these elements into a final list and also enables a graphical representation of what's being built. It proved to be very efficient. Now we are in the phase to industrialize the prototype. The second case of inspection of buildings has a quite ambitious goal to transform passive constructions into smart structures that would be able to not just inspect their inner state, so to speak, but also to take care of themselves. Our approach was to observe nature and create a swarm of robots that would then continuously inspect, analyze, make decisions, and also maintain or even rejuvenate the building. Meaning that this swarm of robots would be part of the structure actually. Now, the approach of biomimetic was used in many parts of this development or stages. One was, for example, climbing. We know from nature that some animals, like the gecko, can easily climb vertical walls using van der Waals forces and not glue but stick to the wall. Some research teams have already used this approach in building artificial geckos that are able to climb. We also observed nature regarding the flying. Flying robots are actually quite popular. But then we also use the biomimetic approach in communication between these individual robots. And here this swarm principle has been used, which, for example, ants used in food gathering, home building, and so on. At the same time, we considered an approach where we would have specialized robots that would actually work together. The first variant was like have very different specialized robots that would collaborate, where, for example, for inspection, flying robots would be used, but for the maintenance, some climbing robots and so on. The other approach, the variant B, was different, because here we had a basic modular robot that is able to combine into various transformers, as we call them, and which would then be able to also to create some climbing robots or get together and create temporary structure support if it would be needed in some dangerous situations. We developed a prototype that behaved quite interestingly. But the point here, of course, is that I want to emphasize this innovative approach, this out-of-the-box thinking in solving problems. The third case is probably the most out of the box of all of those three, because we created the concept as a response to this negative environmental impact using some technologies that weren't actually there 11, 12 years ago. And as you will see, even today, the concept is still more or less theoretical. So our approach was to use nanorobots, but in our case, biological nanorobots that would be able to extract carbon from CO2 from the air and use it to build compact carbon material. How would we do that? We would use light as the source of energy. Now imagine on that surface there are those nanorobots that get the light and use it as a source of energy, but also as code kind of instruction that tells them what kind of material to build. Carbon nanotubes can have various characteristics depending on their geometry, the geometry of molecules, and so on. So they can be electrically conductive and have other properties, different properties. Well, is this possible? Or is it just science fiction? Well, what are actually the requirements? First of all, we need a very detailed, complete building information model. BIM technology is quite mature already, although not yet as complex as we would need it, but almost there. The second would be to transform the existing BIM model into a production model, which means to transform each element in a way that we would have carbon nanotubes with those specific characteristics, including such characteristics that would make this material temporary. So it would dissolve back into CO2 after some time. That would make it possible to build openings, not just solid compact material. And finally, the model goes from bottom to up through slices, very similar to 3D printing, whereby each slice is projected down to the surface where we have those nanorobots that actually build the material and the carbon material. The second requirement would be a light projector, very stable, but it's not impossible. I mean, we do have the technology for this. Another question is compact carbon nanotubes as a building material. Well, what we see on the picture is still a theoretical model, but possible to build. A more tricky question is whether nanorobots can do that. And we, as I mentioned, don't think of mechanical nanorobots. Whether this would be possible, I don't know. But let's see the other perspective. Can we have nanorobots that are powered by light? And can we make them extract carbon from CO2? Well, looking into the nature, plant cells do exactly this. They use light as the energy, and they do extract carbon from CO2. So we can check these two requirements. But can we teach them or control them by using, let's say, various light frequencies? There are projects that used Escherichia coli, a bacteria, to behave according to a specific instruction using light, various light frequencies. So this could also be checked, like it is possible. The fourth requirement is more problematic. Are there any bacteria that are able to create carbon nanotubes? To my knowledge, not yet. But there is research going on that shows the very many possibilities how to use bacteria to build different materials and behave differently. So we can expect in the near future to have also bacteria that would be able to build carbon nanotubes and such meshes. We are still observing the research in this area, and well, once these basic technologies are available, I believe that nano to meter scale building will become available as well. It did require quite some out of the box thinking, yes. Interdisciplinarity, definitely. Biology, physics, well, many disciplines. But mainly we need open-mindedness to get to innovative solutions. And this is also my message or experience to all the professors and researchers at your universities, to try to combine this open-mindedness into your curriculum or into your teaching, actually. The other very important approach is teamwork, because no single person can nowadays hold all the knowledge from the vast knowledge as it was possible a few hundred years ago, where we had Da Vinci or other geniuses who were able to know it all. Today, this isn't possible anymore, so we need teams. So what do we need to teach our students to be able to create innovative solutions? First of all, to understand well the basic principles of their own disciplines, of course. Then to master the key technologies in their field, to be able to engineer something, to build things together, to be aware of relevant other disciplines like biology, sociology, or other engineering disciplines, but also to be able to work in interdisciplinary teams. We can achieve this through projects, especially if we invite students from various faculties or various programs to build teams. We've had very good experiences with our solution design summer school, where we have students from various countries, various cultures, and of course various disciplines, and they came to wonderful solutions. So, of course, to be open-minded and creative, which would be my final suggestion to you and your students. So, I wish you very successful running of the new programs, and with this I would conclude my lecture.